Let's break down DeepSeekMath and the reinforcement learning trick buried inside it. Group Relative Policy Optimization, GRPO, a way to train a model to reason without ever building a critic network. This one quietly grew up to become the engine behind DeepSeek-R1. To teach a model math with reinforcement learning, the recipe sounds simple. Let it write an answer, reward it when it's right, nudge it to do more of that. But the standard method, PPO, hides a second neural network inside it. Not the model you care about, a whole extra one, roughly the same size, whose only job is to guess how good each step was. You train it, you store it, you run it, every single update. Half your reinforcement learning compute goes to a network you throw away at the end. DeepSeek's question was blunt. What if we just delete it? Group Relative Policy Optimization keeps the policy, kills the critic, and replaces its careful per-step guess with something almost embarrassingly simple, a group of answers grading themselves against their own average. A 7 billion parameter model trained this way hits 51.7% on competition-level math. No calculators, no voting. And the exact same algorithm later became the reinforcement learning core of R1. So over the next 20 minutes, we're going to build GRPO the honest way. Start from PPO, walk its objective term by term, plug in real numbers, write out the pseudocode, and watch an entire neural network disappear. Start from the ground floor. We have a policy. That's just our language model, with weights theta. Hand it a math question queue, and it samples an answer O, one token at a time. A reward function scores that answer. 1 if the final result is correct, 0 if it isn't. Now we want to reshape the model so it produces more of the good answers. The tool is the policy gradient. Push up the probability of the tokens inside high reward answers. Push down the rest. But there's a catch that wrecks the naive version, variance. If every correct answer just gets a reward of 1, the gradient can't tell a brilliant solution from a lucky guess. They both simply look good, and the learning signal thrashes around. The fix is to stop asking was this good and start asking was this better than expected. Subtract a baseline, a reference level of reward you'd have gotten anyway, and keep only the surplus. That surplus has a name, the advantage, written A. And basically everything in PPO and GRPO is a single fight over one question. Where does that baseline come from? PPO's answer starts with a clever safety rail. We're updating theta right now, but we sampled our answers from the older weights, theta old, so the two policies disagree, and we correct for it with an importance ratio, rho. The new policy's probability of a token divided by the old policy's probability of that same token. If rho is bigger than 1, the new model likes that token more than the old one did. Multiply rho by the advantage, and you have the raw objective. Reinforce the tokens the new model favors, in proportion to how much better than baseline they turned out. But raw importance ratios can explode and blow up training. So PPO clips. It takes the minimum of two things, the honest term, rho times A, and a clipped term where rho is pinned between 1 minus epsilon and 1 plus epsilon. In plain words, you're allowed to move each token's probability, but only so far in a single update. Step past the fence, and the gradient flattens and stops pulling you further. It's a trust region, enforced with one little min simple, stable, effective. There's just one quietly expensive word sitting in the middle of it, the advantage, AT, 1 value per token. Where does PPO actually get it? From a second network, the critic, also called the value model. PPO estimates the advantage with generalized advantage estimation, GA, and GA needs a function V that predicts, from a half-finished answer, how much total reward to expect from here on. That predictor is not free. In language model RL, it's typically another transformer about the same size as the policy. So now you're training two big models locked together. Double the memory to hold them, double the forward and backward passes, plus extra machinery to keep the critic's targets from drifting. And here's the cruel part. The critic's job is nearly impossible in this setting. The reward only arrives at the very end, one number, right or wrong, after hundreds of tokens. From that single late signal, the value model is somehow supposed to assign a sensible score to every intermediate token. Getting that per token estimate accurate is genuinely hard, and when it's off, it quietly poisons every advantage computed downstream. So PPO pays for a whole extra network, and still struggles to train it well. That is exactly the tax GRPO refuses to pay. The authors name the problem directly. Here's the move, and it's beautiful in how little it needs. Instead of building a network to guess the baseline, GRPO just samples more answers. For a single question queue, draw a whole group. G outputs, say 4 for our examples, or in the real runs, 64. Score every one of them with the reward model, giving a little set of rewards, R1 through RG. Now the baseline writes itself. It isn't a network's prediction anymore. It's the group's own average reward. Each answer's advantage is simply how far it beat, or missed, that average. Land above the group mean, you get a positive advantage, and every token in you is reinforced. Land below, negative, push down. And to keep the scale sane across easy questions and brutally hard ones, they also divide by the group's standard deviation. So the advantage of answer I is Ri minus the mean, all over the standard deviation. That's it. It's a z-score. The answers grade themselves on a curve, and every token in a given answer inherits that one number as its advantage. No value model, no GA, no second transformer. The single most expensive component in PPO just got replaced by a mean and a standard deviation. Now the full objective, built one piece at a time, and notice it's really just PPO wearing the group idea. Outermost layer, average over the group, 1 over G times the sum across all G answers. That's the relative in group relative. Every answer is judged inside its own cohort. Next layer in. For each answer, average over its tokens, 1 over the answer's length times the sum over positions T. Pure bookkeeping so far, average over answers, then over tokens. Now, sitting inside those sums is an object you already know cold, the clipped PPO surrogate. The importance ratio rho, now indexed by answer I and token T, times the advantage, the minimum of rho times A hat, and its clipped twin, exactly the trust region from before. The only thing that changed is what feeds the advantage, not a critic's estimate, but our group z-score, A hat sub I, shared by every token in answer I. And then, tacked on at the very end, one new term, minus beta times the KL divergence between the current policy and a frozen reference model. That's the leash. It keeps the model from wandering too far from where it started while it chases reward. Same skeleton as PPO, group baseline in the middle, KL on the outside. That entire line is GRPO. Let's make it real with actual numbers, because the whole thing turns on one little calculation. One question, a group of 4 answers. The reward model scores them. 1.0 for a clean correct solution, 0 for a flatly wrong one, 0.8 for a mostly right attempt, and 0.2 for a mess that stumbled somewhere. First, the baseline, the group mean, 1 plus 0 plus 0.8 plus 0.2, all over 4, equals 0.5. Then the spread, the standard deviation of those 4 rewards works out to about 0.42. Now the advantages, each reward minus the mean, divided by that spread. Answer 1. 1 minus 0.5 is 0.5, over 0.42, gives plus 1.19. Answer 2. 0 minus 0.5, over 0.42, minus 1.19. Answer 3 lands at plus 0.71. Answer 4, minus 0.71. Now look at what happened. Answers 1 and 3 came in above average, positive advantage, so the gradient pushes every token in them upward. Answers 2 and 4 fell below, negative advantage, pushed down. No network judged anything. 4 rewards, a mean, and a standard deviation, and the model already knows which answers to become more like. That is the entire advantage computation, start to finish. They stated in a single sentence. Back to that KL leash, because GRPO does something subtly smart with it. In the classic PPO recipe for language models, the KL penalty gets folded into the reward. At every token, you subtract beta times the log ratio of policy to reference, and hand that adjusted reward on to the advantage machinery. It works, but it tangles the penalty up inside the advantage estimate, and by extension inside the critic. GRPO pulls it back out. The KL is not shaped into the reward at all anymore. It's added directly to the loss as its own clean term, so it never touches the advantage. and they estimate it with a particular unbiased formula, the K3 estimator. Take the ratio of reference probability to policy probability, subtract the log of that same ratio, then subtract 1. That little expression has two properties you want. Its average equals the true KL divergence. That's the unbiased part. And, unlike the naive log ratio, it is guaranteed to be greater than or equal to 0 for every single sample. So the penalty is always a genuine pushback toward the reference, never a negative fluke that accidentally rewards drifting away. Cleaner signal, lower variance, and no entanglement with a critic you no longer even have. Let's write it as an actual loop, because it's shorter than you'd guess. Outer loop, over training iterations. Set the reference model equal to the current policy. That's the frozen anchor the KL term measures against. Inner loop, over steps. Grab a batch of questions and freeze the current weights as the old policy. Theta old, the one you'll sample from. Now, for each question in the batch, sample G outputs from that old policy. Score all G of them with the reward model. Compute the group's mean and standard deviation and turn each reward into its advantage. Reward minus mean over standard deviation, the one number every token in that answer will carry. Then take a few gradient steps that maximize the GRPO objective, the clipped importance ratio term weighted by those advantages, minus beta times the KL to the reference. Apply the update, move to the next batch, and optionally keep refreshing the reward model as the policy gets stronger. Now scan the whole loop for a value network. Sample, score, normalize, step. There isn't one. Every place PPO would have spun up a critic, GRPO just computes a mean. That absence, that missing box, is the entire contribution. Put the two side by side, and the whole paper compresses into one swap. Both algorithms share the identical skeleton. Sample answers, form an advantage, feed it into the same clipped surrogate, take a trust region step. Everything is shared, except one box, how you get the advantage. PPO's box is a second neural network. Feed it a partial answer. It predicts expected future reward. GA turns that stream of predictions into a per token advantage. Powerful and general, and it costs you a whole extra model to train, tune, and store. GRPO's box is arithmetic. Sample a group, subtract the mean, divide by the standard deviation. That's the box. Same trust region, same importance ratio, same clip, a different baseline. And because providing that baseline was the only reason the critic existed in the first place, deleting the critic doesn't break anything downstream. The group already supplies the reference level the value network used to laboriously guess. One box changed, and half the compute, half the memory, and a big chunk of the training instability walked out the door with it. One refinement worth knowing. So far we've used outcome supervision, a single reward at the very end, and every token in the answer shares that same one advantage. That's fine for short problems. But a long proof might be flawless for 20 steps, and then blow it on the 21st, and outcome supervision blames the entire thing equally. So GRPO also supports process supervision. A reward model scores each reasoning step, not just the final answer. You normalize all of those step rewards across the group the same way, and each token's advantage becomes the sum of the normalized rewards from that step onward. Now credit lands where the good reasoning actually happened, and blame lands on the step that broke, while the group relative baseline carries over completely unchanged. And there's a longer game, too. A reward model is only really trustworthy near the kinds of answers it was trained on. But as the policy improves, it starts producing solutions the reward model has never quite seen, and its scores begin to drift. So GRPO can be run iteratively. Every so often you take the policy's fresh samples, use them to keep training the reward model, mixing in a slice of older data with a replay buffer so it doesn't forget what it already knew. Then you reset the reference model to the current policy and continue. The reward model, the reference, and the policy all advance together, in rounds, instead of trusting one frozen judge for the entire run. That's GRPO, rebuilt from the ground up, critic deleted, and the math still checks out. Quick breath. If watching a whole neural network vanish from an algorithm is your idea of a good time, like, subscribe, and send this to the friend who's still budgeting GPUs for a value model. Because we've now explained how DeepSeekMath learns, but not yet where its raw math talent actually comes from. That's next. So where does a 7 billion model get world-class math skill? Not from the algorithm, from the data, and the way they mined it is a small masterpiece of bootstrapping. The open web is full of mathematics, drowning in noise. Step 1. Grab a seed of known good math pages. They used open web math and train a fast, cheap classifier, fast text, to recognize this reads like math. Step 2. Sweep that classifier across Common Crawl, 40 billion deduplicated web pages, and recall everything that scores high. Step 3. Rank by score, and keep only the top slice. Now the clever part, the loop. Look at which web domains the classifier keeps pulling from. Have humans annotate the genuinely mathematical URL patterns on those domains, fold the newly found pages back into the seed corpus, and retrain the classifier sharper than before. Each round recalls the math that the previous round missed. After 4 iterations, they'd pulled 120 billion tokens of real mathematics out of the web, several times larger than any math corpus before it. And then, crucially, decontaminate. Strip out anything that overlaps the benchmarks, so the test scores are actually earned, not quietly memorized. The paper closes on a genuinely clarifying idea. Take all the ways we fine-tune language models: plain supervised fine-tuning, rejection sampling fine-tuning, its online variant, DPO, PPO, and GRPO. And up front they look like a zoo of unrelated tricks. But write down each one's gradient, and they all share a single template, a source of training data, and a coefficient sitting out front that says how hard to push each example up or down. That coefficient is the only thing that genuinely differs between them. Supervised tuning trusts every example equally. The RL methods weight each one by a reward-based advantage. Seen through this lens, GRPO isn't an ad hoc hack at all. It's one principled choice of gradient coefficient, with the groups serving as its baseline. And the payoff is real. The base model, before any of this reinforcement learning, already scored 36% on competition math, beating a 540 billion parameter model more than 70 times its size. Then instruction tuning, and then GRPO, and the numbers climb again. Grade school GSM 8K goes from 82.9 up to 88.2%, and competition-level math from 46.8 to 51.7. The first open model over 50, no calculators, no majority voting. And GRPO matches or beats PPO on these tasks while training a single network instead of 2. Cheaper and better at the same time, which is a combination you almost never actually get. For the record, it's worth asking which ingredient actually did the work, because we changed 10 things and it got better explains nothing. So pull them apart. First, the data. Swap the DeepSeekMath corpus back out for the older math datasets, and the base model's scores collapse. The 120 billion token pipeline is doing real, load-bearing work, not decoration. Second, the RL step. Start from the exact same instruction tune model, and GRPO lifts every benchmark, including out-of-domain ones it never trained on, which tells you it's sharpening general reasoning, not just memorizing the training questions. Third, the head-to-head. GRPO holds even with PPO on final accuracy while running one model instead of 2, so you're not buying the savings with worse results. So the story isn't one magic trick. It's a great corpus that builds the raw ability, and a cheap, stable RL method that reliably squeezes more reasoning back out of it. Each piece earns its place in the pipeline. So here's the whole thing, in one breath. Mine a mountain of real mathematics from the open web, 120 billion tokens, pulled out by a classifier that trained itself sharper each round. Instruction tune the model, then reinforce its reasoning without a critic. For each question, sample a group of answers. Reward each one. Subtract the group's mean to get the baseline. Divide by the standard deviation to get the advantage. Feed that into the clipped PPO surrogate, and keep the model honest with a KL leash added straight to the loss. No value network anywhere. The group is the baseline. That is group relative policy optimization. PPO with its most expensive organ removed and replaced by a class curve. It made a 7 billion model do competition math at 51.7%. And not long after, that very same idea, scaled up, became the reinforcement learning engine inside DeepSeek-R1. the one-line version. In PPO, the expensive part was never the policy. It was the critic, a whole second network just to estimate a baseline. GRPO realized a group of answers can serve as its own baseline, so it deleted the network and kept the learning. Cheaper reinforcement learning, sharper reasoning. And it leaves a strange, good question to sit with. This model got better at math by comparing itself to other versions of itself on the same question, over and over, with no external judge of what a good step is supposed to look like, just relative standing inside a group. How far does that kind of self-competition go, all on its own? That's my read. Tell me yours. Until next time.